morning, everybody. How are you? Well, it's great to be here. I wanted to focus my session on some of the learnings that we've had at Intel over the past decade. A little bit about me. I've been with Intel for over 20 years, and pretty much that entire time focused in on data center technology. So I've seen a number of different waves in evolution, the move from mainframe to client-server computing, the rise of internet, the rise of cloud computing. We're really on the precipice of yet another transformation in the data center. And I wanted to share some of my thoughts for those of you that are planning, what is it that the data center means in the future? What is it that are some of the changes in the infrastructure itself that you might want to be thinking about? And mostly gleaned from some of our recent learnings about dealing with hyperscale data centers. Now, some of you may be thinking when you think hyperscale, you're thinking just the largest cloud service providers. But really, our view of the world is that you will either be doing computing at scale in the future, or you will be using somebody else's scale. And so really thinking about what that means, what the data center means to your business, and how to also make sure that as you're planning ahead, what are some of those inflections that you might want to think about from an infrastructure perspective. So let me just start with the backdrop here. A quick look at the trends that are driving the infrastructure change and the move to hyperscale. So first of all, the world has moved from something that has been driven by client devices and human interaction, and we're rapidly moving to a world of connected devices. So the amount of data that we expect to see generated in the next 2 years is going to be 10x of every piece of data that's been collected so far, and that just continues to evolve like a Moore's law of data growth. And that's going to be driven by intelligent devices such as autonomous driving, such as drones, intelligent factories. The world is being built out of IoT, and that's going to generate a tremendous amount of data. But as that happens, the infrastructure needs to change, and there are sort of three big inflections that we see. The first is the move to cloud computing. And when I speak of cloud, I talk about it from a deployment model, not necessarily meaning that you're public or private, but that the infrastructure itself, the compute, the network, and the storage needs to be pulled together, automatically provisioned, and that's something that's dramatically changing the way that infrastructure is deployed and managed. The second is the network. As we move to 5G and network infrastructure that's optimized for these billions of connected devices, we have to move to a place where the network itself is more intelligent, and I'll talk about this in a bit more detail. But the actual data center itself isn't just connected by the network, it's running network workloads, such as NFV. And then the third piece is the growth of AI and analytics. And I liken this, when I talk to audiences like this, to the rise of cloud computing. I remember back in the day, it's about 2007, 2008, cloud computing first became something of a buzzword. And I remember people rolling their eyes and thinking it was a path, and nobody knew how big it was going to be. We would make our own forecasts, and I can tell you that every year that forecast raised higher and higher and higher. And I see that happening now with artificial intelligence infrastructure. The rate of change, the growth of data, the need for real-time analytics, all of that is driving a tremendous amount of compute power. So those are some of the big macro drivers that are forcing us to look at infrastructure. And part of the reason that I believe that by 2025, 80% of the workloads that we see across the data center will be deployed in hyperscale data centers. And again, when I say this, I don't just mean large cloud service providers. I see hyperscale as any infrastructure where thousands of servers and a tremendous amount, petabytes of storage, are being consumed on an annual basis. And I see this happening not just in cloud service providers, not just big infrastructures as service providers, SaaS providers, consumer technology. I see huge build-outs happening right now to go support IoT. We see industrial equipment manufacturers doing that. We see a tremendous amount of build-out in financial services, of course. Anything where there is scale, we consider this to be a part of hyperscale, and therefore hyperscale design may be relevant to you. Any telcos here in the room, comm service providers in the room today? A couple of folks. hyperscale and both a cloud infrastructure for the core of the operations, but also seeing the network moving to a cloud and a hyperscale model. And also not thinking about cloud as being something that's centralized in a data center, but as we see the move to IoT and an intelligent edge, the cloud is moving out. I hesitate to use the word fog, but it is definitely something that we see as having a progression from core data centers to central offices all the way out to the edge. And so this design for scale, this design for applications at scale has to be fundamental. And it changes not just the way that software is provisioned, not just the way that the applications are being written or the infrastructure is deployed, but the fundamental principles of the data center design itself. Now, hyperscale used to be simple because the way it was deployed was you took one server box and you just multiplied it out. It was homogeneous computing. And the idea is that the only way to go manage infrastructure at scale was to be able to replicate the same fundamental computing network and storage building blocks across the entire data center. And I say simple kind of half smirking because obviously the software and the management to be able to deploy at scale is certainly not simple. But now it's getting even more complex, as I mentioned, with the rise of, in this transformation in different workloads, we also move to a world of heterogeneous computing. And what I mean by that is the infrastructure, the computing infrastructure, it's not going to just do your business applications, your CRM, your databases across your corporation. It needs to overlay new workloads. As I mentioned, the transformation in the network. If you look at how many hyperscale data centers are deployed, there's a fundamental principle that the cores, or the compute power, needs to be the scarce resource. That is what they monetize, or that's what delivers the application performance. That should be the limiter. The more we see a rise toward hyperscale in this build out, the more that we see network infrastructure needing to be offload and accelerated. Switches and the intelligence of a network that needs to be able to do more east-west traffic, it isn't sufficient to just rely on the network or the comms infrastructure itself. So we see a huge driver in the amount of compute. And of course, we need this infrastructure to be able to run the analytics. And you could run it on general purpose compute, but we see more and more that driving time to money requires an acceleration of algorithms and optimization that may not be the same as general purpose compute. And when you look at things such as visual computing, if anybody's doing inference out at the edge or looking at visual applications or media delivery, those are a completely different set of workloads. So it's really this diversity of workload that's going to require us to deploy infrastructure in a cloud environment that's heterogeneous. And so the infrastructure and the workload orchestration and provisioning is going to need to know how to go allocate those resources efficiently and effectively. And the infrastructure itself, with those that try to deploy a homogeneous infrastructure, they're fundamentally not going to be competitive or able to compete. In this world of these high growth workloads, in dramatically shifting workloads, the infrastructure has to be optimized for those workloads. And so the complexity as we see these workloads growing is exponential. And if we don't have a way to orchestrate workloads, to understand fundamental resources, to understand how the applications perform, then we can't have a data center that's cost effective. A data center that's not cost effective isn't going to last too much longer. Again, it goes back to my fundamental principle. You can either operate at scale or you're going to wind up operating in somebody's operation at scale. So it's time to rethink the fundamental data center. And with all this complexity going on, it's kind of remarkable that the building block of the data center, the two-socket server, hasn't changed in the 20 years that I've been working at Intel. We originally invented this form factor so that it could fit underneath desks. Some of you may remember deploying, email servers underneath desks. And the idea is that you needed to have a building block that could be used for a wide range of applications. And at some point in time, the most we could really think about was that you'd have two processors that were actually working on a small database workload. So what's happened is that's become the fundamental building block of the hyperscale data center. And it doesn't matter whose data center you look into, the largest cloud service providers in the world, they're still taking that same fundamental commodity building block and stringing thousands or hundreds of thousands of those together. And this may resonate with some of you because I'm sure you're trying to figure out how to go do that, how to build very, very wide networks and tiers of your networks to be able to converge all of these things together. It fundamentally doesn't make sense, and it's not something that's going to scale in the world of hyperscale. And what it needs as we move to hyperscale and we think about different layers of the data center, thinking of the infrastructure and the hardware, and then having a provisioning layer to be able to go deliver infrastructure as a service. If you want to deliver infrastructure as a service, you certainly can do the model that we see today, which is taking many independent compute hyper-converged nodes and trying to slice them up into pieces of pizza and figuring out how to shove workloads into them. The result of this is even best in class seeing about 50% efficiency and utilization. And it goes everything from how the resources within these systems are utilized, stranded compute, stranded memory, stranded power. It's just fundamentally not efficient. What we have to move to is a rack scale infrastructure, and this is where we're driving the evolution toward. A rack scale infrastructure that's composed of different pools of resources. And the notion that you can take, instead of trying to fit workloads into the box, how can you provision the resources to be able to go support the workloads? So this is the fundamental shift that's being driven. Now, to make this happen, there are really three components, three things that we need to do as an industry and are sort of the fundamental principles that I see any plan, any strategic plan for a data center in the future to drive. One is efficient resource management, and this is really through software-defined infrastructure, ensuring that there is a overall orchestration layer, a way of provisioning workloads and deploying and managing the infrastructure so that the utilization is high. That means cost competitiveness. That means agility of delivering new services. The second is that the building block should be rack scale and optimized, as I mentioned. And one of the things I'd like to do today is kind of share what I think an efficient rack scale architecture looks like as a building block for the data center. And then also to be able to talk about how some of the changes in technology are going to affect this. So there's some real interesting strategic design points that I see being deployed across the industry. And then the last piece, which I'm not going to talk too much about, is that this is a tremendous amount of complexity. We're talking about changes to compute. There's rise of accelerators and how to go deal with that in an infrastructure, a move to higher performance switches, smart networks, new memory and storage tiers. Some of you may be using optics within the data center to go drive long distances at high speeds. All this complexity. And that's not to even talk about the management and the software layers on top of it. All of this needs to be integrated and easy to deploy. And one of the things that we at Intel are very focused on is making sure that we're both driving open standards in the industry to make that interoperability easier, but also working with partners to make sure that there are fully validated solutions. And anyone who might be interested in this path of infrastructure at a hyper-converged or a hyperscale level that is fully validated, supported, tested, et cetera, can go check out our Intel, what we call Intel Select Solutions, which are partner programs that we have to make sure that both software as well as fully validated scale hardware has been tested together. So let me talk a little bit about what optimized software infrastructure looks like today and the concepts of it. Today, when we look at the infrastructure itself, we want physically to be able to disaggregate. And I'll talk about how rack scale architecture and rack scale design moves in that direction. But what you see on the right-hand side here is the notion of composability, that the best practice today in how we provision workloads, how we utilize the hardware resources, is we virtualize, or we might containerize. All of these are, or function as a service, all of these are steps along the way to utilizing the stranded resources within an infrastructure to provision or share those resources. But still, fundamentally, they all have the notion of taking a fixed hardware or set of resources and dividing them up into some set of chunks to be able to be allocated. We need to move to a world where orchestration layers can identify the resources within the rack and then be able to compose their own virtual machine. That's really truly the only way in which you can deliver the service level and also the efficiency that's required within the infrastructure. And so we're working, whether it's a VMware stack, Microsoft, Azure stack, Red Hat, OpenStack, OpenShift, et cetera, all of these stacks, we're working very closely with the industry to help make sure that we're exposing APIs from the rack itself to be able to have the rack be viewed as these pools of resources that then could be allocated to those types of workloads. This is one of the fundamental shifts that we're driving and looking to see. The second is the actual infrastructure itself. And there are a couple of principles before I talk about some of the changes in the technology that are driving this. But what rack scale design is creating pools of resources that can be efficiently allocated. And I think it goes to reason, as those of you that are data center designers, to think about pools of resources are more efficient to be able to allocate than anything that you have to go ahead and provision. The more that you sort of break things down or have fixed areas, the more that you're likely to be stranding resources. So the idea behind the architecture is to create a tier of compute, where the notion of that compute is that you just are able to go provision as little as you need to beyond just the sheer compute within that system. The rack then itself is also is disaggregating storage as well. And I think this is increasingly important, not just for hard drives, which we've been doing for a while, but as we move to higher speed and more expensive storage class memory. And then we also see the addition of accelerators as well into the infrastructure. And this is going to become a fundamental challenge because there's a catch-22 around accelerators. A few years ago, people would have thought accelerators of any type, whether it's a GPU or an FPGA, within a data center infrastructure was ludicrous. It didn't really make any sense. It was too complex. These are really things that were designed for very, very focused functions. But now, as you see, going back to heterogeneous workloads, there is a demand, there's a need there. But the challenge of it is it can be very prohibitive to put that type of infrastructure across all of the nodes within the data center. And so what we see is disaggregation, again, becomes a way of allowing you to pool those resources and then allow that to be efficiently allocated by software-defined infrastructure. Now, one of the challenges that we also see is that because these workloads are changing, the other benefit of moving to a rack scale design is what we call late binding, meaning that many times the whole data center and the power allocated to the rack and the design of the rack, they're all trying to be done in advance. And many of these things have to be predicted years out to really have an efficiently utilized data center infrastructure. The challenge is that the workloads are moving so quickly, it's very difficult to be able to be that predictive. The result is, again, stranded resources and underutilization years down the line. A rack scale design allows you to say, if I don't have the right type of compute, if I don't have the right type of accelerator, I can find a way to go provision different types of those workloads over time and efficiently utilize it based off of what the actual workload looks like in the future. So there are a few things that are principles around designing a rack scale infrastructure. One of the first is larger compute. There's always this wrestle that we talk about with power efficiency and what does that mean in terms of how we size our server or infrastructure nodes. And I can tell you that without a doubt that the leaders that drive hyperscale infrastructure fundamentally take a notion of larger compute nodes win. Higher performance, higher power, actually pushing that envelope, some of them pushing it to liquid cooling. Why go in this direction? Well, let's just sort of do the math. If I have a larger compute node, To go service my infrastructure, I need fewer of them. If I need fewer of them, I need fewer network connections, I need fewer switches, I have less people managing individual infrastructure. When you look at the total cost of ownership of the data center, one of the fundamental design principles is continuing to drive leadership in the amount of compute in each of the individual nodes. The second thing that we see as a trend is the blurring of the lines between storage and memory. Things used to be very, very simple. You have hard drives for your cold storage. You have a hot or a warm tier with solid state drives. And then, of course, you've got memory, which is servicing the actual real-time compute needs of the platform. And this is going to become another reason why the flexibility in rack scale infrastructure is going to be critical. These design points are shifting. And many of you may be deploying in your infrastructure things such as NVMe solid-state drives, which are very, very high performance, much higher performance potentially than the SSDs that you're driving today, driving a high degree of I/O throughput. But they also can be very expensive to deploy in each of the nodes. And so having a pool of NVMe storage that can be allocated over a fabric represents an opportunity to get that kind of hot tier storage without necessarily having to allocate it across all of the nodes within the server. But that then also affects and changes the amount of hard drives, the amount of solid state drives, and to make things even more complicated, this year we're already sampling our first samples of storage class memory, up to a terabyte DIMM as an example that fits in DIMM slots within standard servers. This actually takes the performance of DRAM, but provides persistence as well. So you can see how the overall hierarchy of what you might do in terms of within the node, DRAM might be shrunk. This new storage class memory might be an expansion within the node itself. And then that might offload some of the hot tiers that you have, allowing you to have an even lower cost storage tier. But all of that's going to be dependent very much on the workload. But the fact that these lines are blurring means that the flexibility within a rack scale design, the ability to disaggregate those nodes and to be able to do late binding decisions is going to be more critical than ever based on the workload and based on the economics. The third trend is around intelligent fabrics. So going back to the notion that now I've got these pools of very high performance compute nodes. I've got storage that's been disaggregated, and some of that storage is very, very high performance. I need to be able to go drive high bandwidth across that. But on top of it, I now want my network to be able to do more of those network workloads. Today, there are still a number of compute cycles that are dedicated to supporting the network stack. And best-in-class hyperscale principles are taking those network and offload workloads and offloading them into smart NICs or FPGAs or other parts of the platform to allow the compute to do what it really needs to go do, again, using that very precious resource efficiently. So more intelligence being driven to the network, more bandwidth being required. The data center itself is longer distances, moving from copper in many cases to optics. And as the price of optics continues to come down and the amount of bandwidth goes up, we're going to see that shift continue to occur. And then, of course, it's connected by intelligent switches to be able to go route that traffic effectively from east to west. So there's a big transformation in the fabric itself, and that fabric needs to not only be able to go drive storage traffic, network traffic, but in an efficient world, moving to the next slide, it also supports accelerator pools. So when we look at the rise of artificial intelligence, there is so much technology, so many different approaches being taken to how to support effective artificial intelligence. And it's almost impossible to say what will long-term be the best way to be able to deploy that technology. But many accelerators are being developed, FPGAs for inference, special purpose ASICs for training applications. But what we see over time is that all of those things can be connected via an intelligent fabric. So having an intelligent fabric that can go drive that traffic effectively then allows you to create a pool, and instead of having to put all of those accelerators bound to specific nodes and use the data center designers trying to figure out how to plan for all of this, having a power envelope that's dedicated to a rack and having the rack being able to allocate these pools effectively. As a result, you're able to go plan for the future without knowing exactly what the future is going to go look like. So I welcome you to learn more, and again, it's been my pleasure to be here today. We're on a very, very exciting journey, and I can tell you beyond a shadow of a doubt that the data center is alive and well. But our ability to develop hyperscale technology that's efficient, that's easy to deploy, that's really something for the masses, is really going to shape the industry. Whether we're able to deploy data centers at scale efficiently will determine how many data centers reside and whether we will have our own hyperscale data centers or will reside in others. I hope you'll get a chance to come see more about what we're doing in rack scale design, and if you're interested, please do reach out. We'd love to continue the conversation. But I also have some of my colleagues here later today talking about management in this very complex environment. So I look forward to talking to some of you later. Thank you very much.